Alright, so now we're going to move on to section 1.2. We're going to continue on with functions, though. That's this entire chapter, chapter 1. Today we're going to be looking at increasing and decreasing intervals, determining if something is an even or an odd function or neither, and also refreshing ourselves on finding zeros and what zeros are. So first let's talk about even functions and odd functions. So we want to recall that an even function is a function that is symmetrical to the y-axis. So if you're given the graph, or if you graph the function, it's usually relatively easy to determine if it's symmetrical to the y-axis or not. What's even easier is to determine if it's not symmetrical to the y-axis. That's usually pretty obvious. You cannot necessarily prove that something is symmetrical to the y-axis by looking at the graph alone, because you might not actually be seeing the entire graph. However, it is pretty easy to disprove that it is not symmetrical. Analytically, we can prove that a function is even or symmetrical to the y-axis by showing that f of x, the function with respect to x, is equal to f of negative x. Odd functions are symmetrical to the origin. So again, visually that's relatively easy to see, or again it's easier to see if it is not symmetrical to the origin. But analytically we can show this, or we can prove that something is odd if negative f of x equals f of negative x. So now pause the video, take a minute, and try to determine if this function f of x equals 6x to the 4/3 minus 5 is even, odd, or neither. Okay, hopefully you came up with that the function is even, but now let's look at why that is. So first let's look at, well, what is f of negative x? Well, f of negative x means this substituted in negative x wherever there's an x. Now I'm also going to rewrite x to the 4/3, remember, is actually the cube root of x to the 4th. So this becomes 6 times the cube root of negative x to the 4th, and then minus 5. But negative x to the 4th, if I raise a negative to an even exponent, just becomes positive again. So f of negative x is actually 6 times the cube root of x to the 4th minus 5, which is also f of x. Therefore, it is even. Now let's just show that it's not odd also. So negative f of x is negative 6 times the cube root of x to the 4th plus 5. This does not equal f of negative x. Therefore, it is not odd. It is possible for a function to be both even and odd, although that is very, very rare. If you want, try and see if you can come up with or think of one on your own. Okay, now we're going to talk about increasing and decreasing intervals. Note the keyword intervals. That tells us our answers are going to be in interval notation. So what are we talking about? Well, we're talking about as the function goes from left to right. So we're specifically focusing on the x values as far as our answer. But what we're looking at is the curve going up or down or neither, because it could be constant as well. So our answers are going to be x values, but what we're looking at is how are the y values changing. So if I look at this function here, I've just made up this function, and I notice that I have a point here and a point here where the function changes from increasing to decreasing or decreasing to increasing. And so this point right here is what we call a relative maximum. This one here is what we call a a relative min. Now we're not going to get into the formal definitions of those right now. That'll come up more again once we get into calculus next semester. But you do need to understand what, or be able to identify a maximum and a minimum. So now the formal definition of increasing, decreasing, and constant. So a function f is increasing on an interval if for any x1 and x2 in the interval where x1 is less than x2 implies f of x1 is greater than f of x2. This is our formal definition of increasing. The same thing is true for decreasing and constant, so I'm going to shorten it up a little bit for those. So for decreasing, a function f is decreasing on an interval if for any x1 and x2 in the interval where x1 is less than x2 implies that f of x1 is greater than f of x2. And then for constant, same thing. A function f is constant on an interval if for any x1 and x2 in the interval, x1 is less than x2, implies that f of x1 equals f of x2. Okay, so now let's look at this function real quick. Well, where is it increasing? Well, it's increasing here up to this maximum, and then from the minimum onto infinity. So it's increasing from negative infinity to negative 3, and then again from 0 to infinity. So I have my interval notation as my answers. Notice that everything now is going to be parentheses at the actual maximum and minimum. It's really not doing anything. If you used brackets at those points, technically it wouldn't be wrong. There are arguments in mathematics on what's correct and what's not. For this, I would prefer if you just use parentheses for everything when we're talking about increasing and decreasing intervals. Then the decreasing is going to be from negative 3 to 0. Now notice that for most functions, maybe I shouldn't say most, but for a lot of functions, here in this case, our domain is all real numbers, or negative infinity to infinity, and the function is constant. So if the function is constant, you're increasing and the domain is all real numbers, your increasing and decreasing intervals should connect to each other. So notice that I go from negative infinity to negative 3 to 0, 0 to infinity, and that covers my entire domain. Okay, now let's refresh ourselves briefly on zeros. So zeros are also called roots, solutions, and x-intercepts. So to find the zeros, the roots, the solutions, or the x-intercepts, we set the function equal to 0 and solve for x. So take a minute, pause the video, and find the zeros of this function. Okay, hopefully I did my math correctly and you got x equals 7 and x equals 2 as well as I did. So how do we do that real quick? If you did not get those answers, I set the original function equal to 0. In this case, since it was a rational function, I multiplied both sides by the least common denominator to get rid of the denominator, so I multiplied both sides by 4x, and the denominator goes away. I end up with 0 equals x squared minus 9x plus 14. Factor that, and I get x minus 7 times x minus 2 equals 0. Set each factor equal to 0. And I get x minus 7 equals 0, x minus 2 equals 0, therefore x equals 7 and x equals 2. If this quadratic did not factor, we could use the quadratic formula or complete the square. If it was something higher order polynomial that we could not factor, then we would have to turn to our calculator. Okay, so now we're going to look at how we can do this on our calculator. So pause the video right now real quick and put this function 8/3 x cubed plus 7x squared minus 9x minus 5 into your calculator as y equals and graph the function. So when you do that, your graph should end up something like this, what you see here. If yours doesn't, then you might have typed something in wrong, so double check your function. Okay, so I'm going to change my window a little bit so that I can see the maximum that I'm missing. So if I go down here, let's make this say 20. And now let's regraph. Okay, so I can see the maximum and I can see the minimum. Now the calculator can find those values for me. So if I do second trace, I can see minimum and I can see maximum. So it doesn't matter which one we find first, let's do the minimum. Alright, it's going to want a left bound and a right bound. That's saying I need to pick an x value to the left of this minimum point and then an x value to the right of the minimum point. Right now the cursor is at 0, which is to the left of that point. So I'm going to use that. For the right bound, I just need something to the right, so let's do 2, because I can see that 2 right here is obviously to the right of that point. It wants a guess, the guess doesn't matter. So I hit enter, I get 0.499999916. Now what this tells me is this is an error in the calculator, or I shouldn't say error, it's a limitation of the calculator. This gave me an approximation. This does mean that the actual point is at 0.5 or 1/2. So I'm going to use that to distinguish my minimum value. So or actually I prefer, let's just use 1/2, sorry. And then the y value was negative 7.417. That's not as important for what we're doing right now. And then we want to find the max, so we're going to do that same thing again. If I do second trace, maximum, so I need a left bound for the maximum, so I'm going to do, let's say, -5. And I'm going to do then 0, because I know that that's to the right. Now I don't want this bounds to contain both of them, so that's the only thing I have to be careful about. The guess doesn't matter. I hit enter, I get -2.25 and 20.3125. So therefore, if I look at this again, I could write my increasing and decreasing intervals. I can see that it's increasing up to this point, then it's decreasing, and then it's increasing again. Okay, so then I can come up with my increasing and decreasing intervals. I know it's increasing from -infinity to -2.25, and from 1/2 to infinity, it's decreasing from -2.25 to 1/2. And that's what I can see here on the graph. Now just to point out, we're not going to go through all of these, but we could also find our zeros on the calculator by doing the left and right bound thing again. I see I have 3 of them. So if I want to find this one, for example, I'll do a left bound of 0 and a right bound of 3, and I get my 0. that's an irrational number. I'm not going to deal with this right now. I just wanted to show you that you can do that. Okay, so we want to make sure we understand zeros, maximums, minimums, even, and odd.